Thank you, Charles, and it's a pleasure to be here. So, like Charles said, we started actually collaborating 2 years ago when Ray was in its infancy. And actually, initially we developed Ray to target these reinforcement learning applications. And I remember we had a meeting 2 years ago, with Ant Financial, and they were actually the first to kind of think about the potential of Ray as a general computing platform. We were a little bit taken aback by their question then. But here we are, and indeed, Ray is becoming a general computing platform. How many of you here have used Ray? Okay, so many of you have not used. So I'm going to talk a little bit about Ray. I'm going to provide an overview. And hopefully, after this, I'll, next time when I'm going to ask, I'll see a lot of more hands raising up. Okay, so let me tell you about why I am excited about Ray. And here is what I am excited. I think there are a few trends which actually lead to the logical conclusion that something like Ray is needed in the future. And this is what are what we are seeing today. So first is the applications are becoming distributed and more complex. The second point I will make is that today there is no good framework for building and running these applications. And the level of excitement here is that Ray has a chance to become the standard for distributed applications. Okay, so that's what he's about. So I'm going to go through all of these points in most of my talk. Again, provide an overview of Ray, and towards the end, I'm going to zoom in on some things which we want to do and future plans for Ray. Okay, so the first point, the applications are becoming distributed and they are becoming more complex. So there are two reasons why applications are going to be more and more distributed, and one is obviously on one hand you have the Moore's law ending, and as you know, and that's compute. And while you hear that also here in China there is a lot of effort on specialized hardware to put the computation boundaries. And we still are going to see rapid growth of the computation for specialized hardware. Not the same things happen with memory, right? The sisters of Moore's law is called Dennard scaling. And according to Dennard scaling, it used to be that you double the number of transistors on the same surface in the same area every 18 months, and the power consumption was the same. So basically the same power, the same area, in 18 months you double the capacity of the memory. This is no longer the truth, so as you are going to now to put more transistors in the same area, you are going to draw more power. So that's a fundamental problem, and with memory again, there are not many tricks you can play. Still, you have a certain number of transistors to store 1 bit of memory. So that's really is like in terms of the what we are going to have, what you are going to see in terms of the improvements in memory, and after some time also in computation, is pretty much going to slow down and stop. At the same time, this is the second reason, is the demands in terms of data processing and machine learning are growing faster than ever. And this is a plot from OpenAI, which basically says what are the computation demands to train the largest model at a given time. So you can see here AlexNet and GoogleNet, sequence to sequence, AlphaZero here, and so forth. On the y-axis, you have the log scale, and basically what this plot says that the amount of compute required to train the largest model doubles every 3.5 months. Remember, the Moore's law was doubling every 18 months when it was used to work. This is more than 30 times faster. So even if the Moore's law were to work like it used to be, we will still have a big problem. So the only way really to implement these applications is going distributedly. okay? And of course, the application also are becoming more complex, and one of the reason is becoming also more AI-centric. Almost every application, they have a component which is AI, right? You know, it's like, it's not only financial applications, there are health applications, even, you know, Salesforce, right? Which is an application for salespeople. They have now an AI component which is called Einstein, right? So everyone is doing that. Right? And so let's look at this application, and I'm going to start with an application that is very familiar to all of you. You are doing this. It's a it's a recommendation system basically, and this is about to promote and to recommend new services and new products from your affiliates to your users. And if you look at the pipeline, again, I'm really abstracting away here, but even this high-level abstraction, I think, is enough to make my point. What do? You get the logs from the users, you process the logs, you do some featureization, then you, based on this data, you are going to train a model and you are going to deploy the model in production to serve the users your recommendations, right? This is what you do. And obviously, and Financial is doing, and many of you Alibaba is doing here, then the question is that how frequently you can retrain the model, because ideally the faster I retrain the model, the better I can respond to the changes in the user behavior, or for instance, trying to figure out what is the impact of a new product, right? If I can learn very fast when I launch a new product, then I can very easily target much faster the kind of users which are more likely to like that product, okay? So how do you implement this today? So really today what you do, you use for each of the boxes some of the, you know, best of breed systems or frameworks, right? Here you may use, you may use Flink, right? Other may use Spark, and obviously Kafka is somewhere in between. It's before, right? For training, you may use distributed TensorFlow, maybe Python distributed, maybe Horobot. And for here, you use another model serving system. Sometimes many companies build their own, or use Clipper or something like that. Okay? So what is the problem with these pictures? And I've seen this picture on your building Spark and with big data. The problem with this is that this makes building these pipelines hard, because you need to build the application. It's an end-to-end application in which you need to integrate different systems. Each system has its own API, maybe has different, you need to program in different languages. Here probably you do Python, here Java or Scala and things like that. So this is it's costly to develop. But then also, if you think about deploying and managing it, it's again is complicated, because you are going to end up with different systems which have their own characteristics, right? And then you here made another great point, which I realize more and more, that it's a real pain if you want to have an end-to-end failure semantics. Is very hard, because each of these systems has its own failure semantics. And ultimately, we are talking about this kind of online learning, fundamentally, right? It's like, the problem with this picture is that the end-to-end delay is going to be not that great, right? Because you need to move the data between different systems. Typically, you move at large granularity, you have different storage systems, different formats, and so forth. And this is one of the simplest application you can think of, because in general, you don't do only training, you also do higher parameter tuning, right? You don't do only serving, you do A/B testing, maybe you do multi-arm bandits, and all these incremental rollouts, shadow testing, and so forth. And as more and more companies, obviously you are doing that for a long time, are using reinforcement learning, you don't only interact in general only with a real environment, but also with simulations, do large-scale simulations. So this is basically what you have to do, right? It's like to implement an end-to-end application, and more of the application will look this way, right? So what do you do today? right? It's again, one thing we've seen, what you do today, you can use these domain-specific best-of-breed systems, right? And here it's a, I have two axes here. Here is a easy to use for these frameworks and generality. And obviously these domain-specific frameworks are easy to use because they provide an API because they target a particular workload. Then generality is a little bit lower, right? You cannot, it's hard to use Spark for distributed trading, so to speak, right? Or you cannot use Horovod for data processing. So now, as long as your application is very simple and uses only on one of these frameworks, things are easy, right? You use a framework, you implement your application full end-to-end, you are happy. However, if there is an application like the one we discussed, you need to stitch together these multiple frameworks, and then it's like we discussed, it's hard to develop, deploy, manage, and the performance is not that great. So this is one way you can build it. What is the other way? The other way, you start with a much lower but more general platform, lower level, but general platform. Think about you use Kubernetes with gRPC and Dockers, right? This is pretty much, Maybe you can do the MPI for communication and so forth. And then on top of that, you build your solution, right? And actually, we are talking about reinforcement learning. I was talking about one of the driver applications. There are a bunch of solutions which uses this one or this one. It's like Horizon, a platform from Facebook. Is kind of a combination between these pictures here. You use kind of Spark for data processing and then some proprietary stuff there. And anyway, so, but of course, when you build these solutions, you are going to optimize for your use case, so the performance will be pretty high. However, the cost it's also very high in terms of engineering and in terms of time to develop. And the many cloud providers, recognize this big gap, and what they came with is these cloud functions. Say for the developer, it's much easier than just doing. Right, just providing you only Kubernetes and like orchestration, and then you do your Dockers, and it's more general than these domain-specific frameworks. So this is good, and this is very successful, actually. It's like many people love it. Amazon is probably pushing the hardest on this. And it's quite easy to do for simple applications like ETL and things like that. However, if you look in terms of generality, it's a little bit lacking there. So just to be very clear, for instance, or to give an example, it's very hard to do distributed trading. Actually, you cannot really do on these cloud functions or serving. But it's even something even more problematic with this. Every cloud provider, because they see this as an opportunity, like as a gap, and something really people want, provides their own API, right? And then obviously some of the customers are worried about locking, right? So they kind of hesitate, right? It's like if I develop this for Lambdas, for AWS, I'm going to be locked there, right? Or whether if I use Spark or something like that, everyone provides kind of Spark, or it's easy to go from one cloud to another. Okay. So really, this was my second point. There is no good platform for building these end-to-end distributed applications, and Ray, I think, has a chance to be that framework. That's what Ray is. What we are placing it. So now let me talk a little bit about Ray. So he claims that Ray is general, it's easy to use, and high performance. Is general, so in some sense what Ray aims to do, and again, we are not there, but this is an idea aims to do, is to go from this world in which you have for different workloads, use different frameworks to support these workloads, to this new world in which you have a unified engine and you support all of these workloads on top of this unified engine by implementing powerful libraries. That's basically what it is. So many people ask me, and sometimes it's hard not showing by example about, well, why do you think Ray can do this, or why is general and so forth. This was happening for the past 1.5 years. And my best answer now I have is the following, is that, and a few of you already heard me giving this answer, but my answer is the following. If you think about all these programming languages, if you look about what are the constructs, the abstractions, the main abstractions, you have functions and classes or objects, right? That's what you have. So what Ray allows you is to, it's transparently execute the classes or instantiate objects remotely, okay? And allows you to parallelize your application in these units of functions and classes, right? A function executed remotely, we call it task. A class or an object executed remotely is called an actor. And by the way, the nice thing what it gives you this one, you used, if you use the Spark or Flink and so forth, in many of the systems you have only typically task, you have stateless computation. For actors, it allows you to have stateful computation. So the state is embedded in the, with the actor itself, so you can have mutable state. So this basically is the bottom line, right? It takes the two fundamental constructs you have in the programming languages today and allows you to transparently execute them remotely, right? And take care of and doing all the management. It's also, it's pretty easy to use, especially for simple parallelization. You can parallelize your code with just a few changes. And one thing we found from talking with people is that actually many of them like Ray because they can take their sequential programs and with a little bit of effort, they can parallelize them. And just to give you a sense, this is a single-threaded high-parameter search. So you're doing high-parameter search. There are around 100 lines of code here. Actually, the program, there are more boilerplates code. And here, in this particular case, you need only to add 7 lines of code in order to now run this program from one core to hundreds, thousands, or tens of thousands of cores, right? And I'm going to talk more about a little bit about this API. But the point to notice here is not that only there are 7 lines of code, but in this particular case, I don't need to change the structure of my program, right? So that's what I mentioned that some people find it very useful. So now I'm going to go into a little bit more details to tell you about what happens under the hood. So this is a simple application. This is a simple program. It's again, you just read from 2 files and you create 2 arrays and then you add them up, and that's the program. Okay, and so in order to transform this program to run it to distributedly and in parallel, first of all, for every function, you want to be able to run it remotely, you add this decorator ray.remote, right? That's the only change. And then when you invoke these functions, which can be run remotely, you are going to also add remote. So that's pretty much it. So let's see what happens. So so now let's run this first line, which read array remote, so file 1. So assume that file 1 is on machines, file 2 is on a different machine. So what Ray is going to do, hopefully in this case, is going to run read array, or is going to run read array on the node which has stored file 1. And this will return, not the value itself, will return a future, right? A future is an identifier to the result of the function, and it will return immediately, right? So right now, you submit the task, this function to Ray, and it returns immediately, right? And this is key because now I can execute the next function, right? The next line of code here, which again will execute remotely another instance of read array to read the files too, right? again, this returns immediately, and then I'm going to add them up, right? You are going to pass to the add the identifiers of the two arrays. So you see, this executes right away, right? And all this computation graph now is submitted to Ray, and Ray is going to schedule all these tasks, and is going to start executing, right? Eventually, you want to get the result, and you call Ray get, and when you call Ray get is blocking call because you need to order results. So you need to, you are going to, the program here is going to wait for the entire disk graph to execute and to get the result. Okay, but notice, but by doing that, at least in this simple case, the two reads are happening, which are probably the most expensive operation here. They happen in parallel. Okay, so that's what it is. And for the actors, it's quite simple. Well, actors is basically this is a counter actor. It's extremely simple, and this is the returns of the methods when you invoke you invoke an actor. The method of an actor also returns identifiers of the results. I'm not going to go more details, but this is to give you a sense what happened under the hood. By the way, you can also specify the number of GPUs or other resources for if you need special resources to run your actor or function on. Okay. This is pretty much it. So now let me tell you a little bit about the architecture. So this is a scalable execution engine. Again, you execute at the core, you execute this dynamic task graph. This is what Ray is doing. And we try to make it scalable by distributing all the key components, including scheduling and the system and program state. Now, the architecture at the high level is quite similar with many other systems you are aware of, and I'm going to point out what are the differences. You have a driver and a bunch of workers, right? The driver will run the programs I shown to you, and is going to run and to task it on different workers. All the drivers on the workers or the workers on the same machines, they communicate through shared memory. And we have using this shared memory implement a distributed object store. So all of these arguments, when you call a task, you've seen in the previous examples, are going to be propagated through this object store. And we use arrows using Apache Arrow for serializing objects in this object store. And for each node, you are going to have a local scheduler. Okay? So this is one difference from systems like Spark or Flink and so forth, who have the scheduler which is associated with the driver or the master node, whatever the name it is. Okay? So this is a distributed scheduler. Because if you have the scheduler on only one node, that becomes a bottleneck. In general, when the driver or see an worker can submit a task or create an actor, the local scheduler will first try to, if there are no constraints, if all the constraints are satisfied and there is enough capacity available on the current node, is going to try to instantiate that actor or to run the task on the same node, right? For efficiency reasons. Of course, if it's not, you are going to run on a different node. So here is another kind of difference from other systems. The difference is that what Ray is doing is having this global control state. So think about the global control state. You take all the state control information in the system and you store it in this global control state. This means you have the objects, you know all the objects where are in the object store. You know which task and functions you can execute. You also, when you invoke a task, you know where the task was executed and so forth. So all the state in the system, except for the value of the arguments or the results, is here. Okay? So this makes the architecture of the system pretty nice and stateless. If a node fails, then all the information you need, for instance, to reconstruct the data on that node, most of cases, it's in this global control state. Okay. The other nice thing in general about this global control state, because you have all the information here, is much easier to build. We haven't built much here, but you know, this is a this is what is our assumption. It will be much easier to build these tools, profiling, debugging, and so forth, because again, you just look at this database. You don't need to go to every node to get the information and so forth. I mentioned you about scalability. Every component is scalable. This global control state is a shared database or key value store, in-memory key value store. Then again, the scheduler is distributed. They share the same information. And then the other thing which is interesting is that a task or a function can create another function or an actor. So a worker can create more work. So this is again different from something like in Spark, where the only one who can create work, who can create task, is a driver. And that's important because even for instance in Spark or in Flink, if you remove the bottleneck points like the scheduler and so forth, then the driver becomes a bottleneck point because it cannot submit enough task fast enough, right? That's the bottleneck. So in this case, you know, it's like if you want to run a huge number of tasks, you are going to say 1 million tasks. You have the driver ask 1,000 workers, each of them to launch 1,000 tasks. So then you have very nice scalability. So this is some of the performance. This is the number of tasks per second. You can versus the number of nodes. You know, it's like it's almost linear. It's again because there is no single bottleneck point. Here you show that for 100 nodes you can do 1.8 million tasks per second, and the latency of local task execution is like 300 microseconds, and of a remote task it's 1 millisecond. So it's quite low, right? This is a task doing nothing. It just returns some results. This is also array, it's compared, you know, we are claiming that it's quite general. So this is array, we claim that array support different workloads. So this is array compared with some specialized systems for serving, training, and simulations. And I'm not going to spend too much time here, other than saying that typically, you know, the higher the better. And at least for these experiments, array matches or exceeds the performance of specialized systems. Okay? So what is the status? The status is that this is what we have today. We have array core, and on top of it we build a bunch of libraries. One, the reinforcement learning library, RLib, and this is actually based on some metrics in terms of the number of contributors, external contributors. This is today I think I mentioned the most popular large-scale reinforcement learning library. Tune is high parameter search library. Modin is a drop-in replacement for Pandas. Pandas is the most popular tools for data analysis for data scientists in Python, right? But that's running on only one core. So this is supposed to, you know, the goal here is that you take your Pandas code, you change one line of code, and now it runs distributedly. And there are many applications. You are going to hear some of them here later, developed here and by other companies. So how we are looking at the adoption? We have a growing adoption. We have over 160 contributors coming from over 40 companies. We have quite a few tutorials at O'Reilly. It's included in AWS SageMaker. If you do reinforcement learning, you can use RLib. In terms of what? GitHub stars, we are doing pretty well, okay? So both in terms of the slope and when the slope started. So, and compared with several popular open source frameworks. And yes, it's used by many companies, including Unfinancial and Alibaba. Any questions so far? Because I know I'm switching gears and I'm going to talk about priorities and what to do next. Yes.
Thanks, Professor. I'm Li Jiexu from Chinese Academy of Sciences. And I have several questions about Ray. The first one is that for a developer, how to determine which function should be changed to remote APIs?
Which what?
Which functions? A program may have many functions. Yes. Which functions we should change them to the Ray APIs?
That's an excellent question. Because the first time the users do it is like they put remote everywhere.
Yeah.
And then they have a function which takes, a few tens of microseconds, and then this is executed remotely, and the program will going to get slower because the overhead of invoking that function is higher than running that function.
Yeah.
So, obviously, we have some blocks. You can profile your program to see which one you have to do to execute remotely. But I think here is where you can do a much better job in terms of tooling. Because, for instance, if you execute a code, if you execute a function remotely, we can measure how long it takes to execute a function, and we know the overhead of calling that function, and we can give you a warning that probably this function shouldn't be executed remotely.
Oh, thanks.
But that's a very good question.
The next question is that if I sometimes I write multi-thread programs.
You write what?
Multi-thread.
Multi-thread.
Yeah. Does the Ray support these programs? How to change them to migrate to the Ray?
So you can write a function in Ray right now, a function or an actor, it's executed in a different process.
Yeah.
Right. Within that one, you can obviously write multi-threaded programs. There will be some implication about fault tolerance and so forth.
Yeah.
But if you are thinking to execute a functions as a thread or an actor, we don't do it now, although there are some discussions with our friends at Unfinancial to do that. We'll see. But that's... but you can write, but it doesn't help. Ray doesn't help you to do the multi-threading. You can do your multi-threading and still the level of parallelism is a process.
Oh, okay. The next question is that if my program has many states, for example, add one, in this case, how to guarantee the state consistency? Because the Ray use many date stores to store the.
Oh, you have an actor and you add one, or what?
Yeah.
How do you get? You mean exactly one semantics or things like that in the case of failure? This is what you mean consistency.
Not just the failures, but also many. My program may access the states to read it. Another one may write it.
Write it.
Yeah.
So if you implement that with an actor, for the actor, we serialized the execution of the methods on the actor. So if you have an actor which to implement that kind of storage and you have read and write, that's going to serialize it. But if you have a functions or actors to write to an external storage, right?
Yeah.
And read from the external storage, we don't help with that, right? Because it's about the semantics of that particular storage.
Yeah. The next question is that does Ray support streaming applications?
Streaming applications. Yes. Yeah.
For example,
not as well, but it will be much better soon. They have very demanding streaming application. They have very demanding streaming requirements at Unfinancial and so forth. But yes, that's a priority.
Yeah.
You can ask them.
Okay, thank you. These are my questions.
Thank you. Yeah, but the plan is to have I'll show you here a little bit. I'll talk a little bit about that. So what are the priorities going forward? So it's again, Ray is not an old project. It's like 3 years, less than 3 years. So there are still lots of things to do. And we think that the main priorities are the following. This is the order: stability, performance, features. Right? So you want to make it as stable as possible, improve the performance, and then add features. And then I'm going to I cherry pick some of the features I understand better. So it's not necessarily the most interesting one. So in terms of stability, one of the problem is garbage collection, right? It's like we have this object store, right? Distributed object store. And there are some use case scenario, for instance, in streaming, in which you have this object used only once, right? You know, and then this pollutes the entire object memory, and then you use LRU for the object memory for the object store to evict the objects. And because if you write a lot of objects which are used a single time, you are never going to use them again. They are going actually to lead to the eviction of the object actually you care and you want to access in the future. It's a pretty big problem. Because then, in some cases the object cannot be reconstructed, in some cases it takes a long to be reconstructed and so forth. And this is a hard problem because you are talking about garbage collection in a distributed system. It's a hard problem. Also, there are some prototypes out there. I'm just saying a little bit about some high-level solution. Actually, this is about single-used objects, right? This is one of the problems I was mentioning to you, is that you call the f-remote and you get the result back, this OID, the identifier to the object, and you do ray get here and you get the object, and that's all. You never, this object now, which was in the object store, you are never going to read it again from the object store, right? You are just going to consume. So you want to identify these use cases, which in some workloads is like 80%, right? Or something like that. So you want to be able to remove it right away from the object store. We have actually a workaround today in which we push this to the application. We have a experimental API, get and delete, I believe it's called, or remove that, and in which you basically, you say, when this you execute, you get the object and then you remove it from the object store. But obviously for general case, you need to do some global reference counting, and this is really hard. It's kind of to be absolutely consistent. And here you can think maybe you can approximate reference counting in the sense that if the object is out of scope, so the real or reference counter is 0, maybe the approximate reference counter can be greater than 0. It's okay, it's a leakage. The one thing you don't want to have is that the true reference counter is greater than 0 and the approximate to be 0. So you want no false negatives, but false positives are acceptable. So this is one thing we are working on. The other one, GCS fault tolerance. I told you this global control store, which keeps the entire information of this in the system. Right now, it's a sharded Redis, and it's not fault tolerant. And we are having a prototype last year, using chain replication. We are also talking about using a library, and there are some experiments using Paxos and Raft replication. We'll see, but that clearly we need to make that fault tolerant. And then, obviously, this is not enough. You probably need to do also to have on top of that, when you have multiple replicas, is to have another mechanism. Maybe here you use etcd or console or some of these systems for leader election to elect the leader, right? It's like if it fails, you want to elect the leader. Stability. It's also object spilling over the disk. So an object right now, when it runs out of the object, object store runs out of space, you just evict objects, right? But we want also, you know, a smarter way is also to push this object to the disk or maybe to a remote storage, right? So that's another one. Performance. I'm moving to performance now. So Ray right now, the backend is written in C++, and the front end, the first bindings was Python. So a lot of functionality is written about the worker functionalities in Python because it's easier to write and easier to develop. However, this kind of is slow, is not as scalable. So now we are, where is Hao Chen? Yeah, Hao Chen there, it's rewritten some of this, you know, Python functionality in C++. It's also, this will improve not only the performance, but it will be make easier to provide API for other languages in addition to Python. And we already have an API for Java. It's another effort going on now. So now the object store is implementing a shared memory. And we want to move to memory map files instead of shared memory to memory map files because this is improved performance and portability. Like for instance, one of the things which was very obvious is like we are talking with these people from Intel about these new memories like 3D crosspoint, non-volatile memory. And when they build this one of the first, when they started to implement functionality on top of it and APIs, memory map files, it's one of the first they implement. So you can, you know, that's an example. The other one is actor communication, and this is exactly with respect to streaming. It's one of the main, one of the main use cases. Look, right now, actor communication is quite slow. It's, I don't know what it is. It's like few thousand of method per second, something like that. But we want to go to hundreds of thousands or even millions. And there are two ways really how to improve the communication: batching, or if you prefer, vectorization. You batch multiple invocation between, if there are two actors which communicate, and this happens if you implement streaming, you just batch many calls. Or we are also exploring the direct actor-to-actor communication. Right now, I didn't show you, but this is you have on each node you have this kind of daemon, which is Raylet, and all the communication is going through that daemon. Now, this will raise problems and questions about what fault tolerance you need to provide, you are going to provide, because if you don't see any of this communication in the global control store, it's very hard. The application needs to deal with the faults. And there are also some security implications. So, but clearly, you know, we may provide, and the plan is to provide this as an option. Functionality, multiple language API support. We have a Java API contributed by Unfinancial, and we probably need, you know, refine it to see what are the lessons learned and how can we improve it. And the next we are looking to add C++ API. So one cool thing here, if we are going to be successful, and I see no reason not to be here, is that you would be able, you know, to run on the same cluster, on the same application, code in Python and Java on the same cluster. I think that will be very useful. Okay. About the new things we are building. We are talking about the serving, and you can do a little bit of serving, but you need to implement all the functionality. But we are looking now, we are adding, and we are working on this new library which to do serving. Build a serving library, and to serve complex pipelines, doing load balancing, auto scaling, fault tolerance, and things like that. Actually, we are very excited about that because we see that we look in the industry all over the place, and we see that the serving, there are very ad hoc solutions for serving. The serving system becomes very complex, and I think that we can simplify the programmability of those and manageability of the system. And streaming, right? We're building a streaming library. We are going to provide a similar API to Flink's API and UDF support and so forth. Now I am done with giving examples about things to do in terms of stability, performance, and functionality. Here I'm talking some more about architecture. So we are talking about, making the storage, some of the storage system for GCS, Google, Global Control Store, more pluggable. Now use Redis. But if you want to use something else. The part of the rewrite for the worker, C++ implementation, it's also to have the transport layer pluggable, how you communicate between the actors. And probably there are more examples here I forgot. And finally, look, I think that we already have these libraries which are quite successful. We are going to double down on those. And I think there are two things here we want to do. Obviously, what I mean by double down on this, obviously to make more robust, to scalable, and improve the coverage. The number of algorithms supported by RLib should increase. The number of algorithms using Tune to schedule the task for high parameter search. We can improve modding. I told you about pandas. Now our coverage is not the full API of pandas, which is a few hundreds of function calls. We are only cover the most frequently used. Okay. And the cool thing here about developing this library is like a little bit like eat your own dog food, because this will will make sure then that this will put pressure on Ray to provide to provide support for building this kind of general applications, because these libraries, each of them has very different requirements because support different workloads. So if we are successful building these libraries on top of Ray, this is another vector to push Ray to become really a general useful platform. Okay. So in summary, again, the reason I'm here and I'm excited, and hopefully the reason you are here as well, is that I think it's a great opportunity. And look, I mean, this is pretty clear. I mean, at least the first two, the applications are becoming distributed. No question about that. They are becoming more complex. And there is still really no good framework for building and running these applications, right? And it's for good reasons, because we didn't need this before as much. If you think about the history of distributed application or parallel application, it started maybe 20, 30 years ago. It was high performance computing. Why? Because you wanted to run simulations on these big computers, right? This is what you do, like ARM simulations or whatever it is. Then it was big data. Why? Because you wanted to analyze big amount of data. That's the Spark and so forth, right? Right? Then you have more recently training. Why? Because you want to train, and train takes forever. So people, you build this. This is very natural. You build these systems for the new workloads, which are, but now you have many of the things which are distributed, and you want to stitch them together. It's very hard to do that. So I think that this is a gap, and it will be filled by a system in the future. I have little doubt about that. Now, I think that Ray has a genuine chance to be that system. We'll see. But the demand is there, and the need is there. I think we are at a strong start, and but still huge number of things to do. And, we hope that we can realize this opportunity together. Thank you.
Thank you for the presentation. I have a couple questions, but I think you already answered those questions in your the summary, in those improvements. So, but I'll just repeat my question. The first one is, I think the whole Ray framework heavily rely on the share memory, and all the invocation is rely on all the data, or also all the functions are in memory. But how do you think, because I see there's an improvement is changing to using MM file or MM map to improve the improve the portability. But my question is, once if the data going to disk, and what do you think the performance degradation will happen, and how much would be left?
Depends how much data is going to disk, right?
Yeah.
And how fast is the disk?
Yep. So basically the question is, I know there's a lot of research around using memory as the, I would say, heavily rely on memory for the computation. But in reality, in a lot of internet companies, all the data is beyond the capacity of the memory you can provide. So like how real the Ray framework can be used in large-scale internet company. So I think that is the first question. And my second question is related to that, but slightly different. Right now, the function is basically you rely on an object storage. If all the objects are locally, then you get really good performance. If the object is remote, you need to copy the data. Based on my understanding on the paper, you need to copy the data to the local scheduler and invoke the functions. So my question is, if your state, I would say the object became very large, how what is the plan for Ray to improve? Thank you.
Okay, so let me start with the second question. So I think that, so if you invoke a function on the same node, and if you put the argument of that function in the local memory, then the function you call will read the data from that memory. There is no other copy, right? That's number one. Number two, actually, there is an optimization, actually, in which when the arguments are small, the arguments are inlined. So you send directly with the method invocation, with a task invocation. So it's inlined. So in that case, it can be as efficient as you can get. The third thing is that you ask about what happened if I am going to go to run the function on a different node. And I have a big, the object, it's on a different node, right? So in that case, there is no other way than feeding the data, moving the data to where the function runs. With the latest version of Ray, we do use parallel connection to improve the speed at which you are going to move the data, but you still move the data. What we, in some cases you may think about, but we don't do that, and because it's tricky. You may think that maybe for some application you can start consuming the data before it's totally transferred, all of it. We don't do that. First we need to transfer the data and then we consume it. But I don't see what you can do in that case. Now, your other question is about, the first question is about what happens for really large application with a large amount of data. I think there are two kinds of applications, like applications which are very latency sensitive, like streaming and so forth, or maybe some very interactive queries, and applications which are kind of more batch oriented. For applications which are very time sensitive, you do hope that their data, the working set, they fit in memory. Like for streaming, I would expect, it's fitting in memory. If you do the garbage collections the right way, right, and you don't have this memory pollution. I think for other data, there is, if you have, 10 times more data than memory, there is not much we can do. The one thing I can say we can do is that, although it's not easy, Ray provides you the ability to control to have a very deep control, you can control on the scheduling. So if you know about the application and if you know about the data where it's located, you can actually control where to execute the computation and so forth at a much higher degree than any other existing systems. Now, with that control comes complexity, right? Because I let you do it. But you can do it. So so the summary here is that if the application it's you process huge amount of data and you have to do it. I can't help directly much with that. What I can tell you is that at least Ray will not stay in the way to do your smart optimizations.
Thank you.
Awesome. My name is Alejandro from Selden Core. And that was an excellent question because it actually introduced the question I was going to ask. So the question is basically, I think looking at Ray, often it seems quite orthogonal to Spark, yes. Technologies like Spark. However, specifically with the thing that you said, my question is, how do you see Ray in relation to Spark? And I guess more generally, given companies like Databricks are using that as their core engine, the need for data science requiring this sort of like batch and horizontal scaling has made this type of libraries more popular, but they fall apart when it doesn't fit in memory. How do you see Ray in relation to Spark? Also Spark streaming and all that stuff.
Yeah. So look, I think that the way, obviously, I know both systems very well. So think about. I'm just trying to find analogies because I can give you a long answer and more precise answer. But the analogy is like, so Ray is much lower level. It's providing a much lower level, right? And provide a much more flexible and computation model, but it's clearly lower level. Like for instance, in the case of Spark, it's data parallel. It's a simpler computation model. It's bulk synchronous processing, but the complexity is hidden under the hood, right? I write what appears to be a sequential program, and all the parallels is under the hood. Which is both the power and the weakness of that model, right? And with Ray, I'm exposing you this kind of fine-grained parallelism you can control. You can have nested parallelism. You can ignore the results from if I wait for results from any task, I can ignore them. You cannot do that in Spark for good reasons. So it's again much lower level. In some sense, if you think about a Spark will be something like a Pandas or some SciSQL or something like that, and Ray is something like a Python, right? So it's a programming. It's much lower programming language. Even if you talk about the Databricks, obviously I know that very well. If you look in terms of the users, Databricks is targeting is data scientists and data engineers. Ray is actually targeting fundamentally. If you ignore the libraries, you target software engineers, right? So that's what the way I'm thinking about that. It's like something like Spark and Databricks is the next evolution from the database. Database management system is now data processing. This is more, it's again lower level. It's like if you were to make, say, Python, which is a general language, or Java to work well distributedly, what would be that thing to be? Would that thing be? So that's what. So, like in theory, you can, even implement and hopefully something like Spark on top of Ray, it will be hopefully easier to implement. Although, it's still a huge endeavor. So that's one other way to think about it. Right, and that's why in some sense, well, the main original use cases about reinforcement learning and all of these things was it's very hard to do that with in a bulk synchronous processing system.
Yeah, my first. Thanks for sharing. And I also have several questions. My question is also about the memory. First of all, that given that you keep all the objects in a table and you just delete delete all the object when you see the get or destroy. And I saw that some of our applications, for example, the dynamic neural network or something like that you cannot determine your network or your object from just the beginning of the data. I mean that when the application is running, that all the object is created by iterate. So you cannot just keep all the object into the database once in the beginning. When you scan all your program, you cannot determine it's not determined.
You cannot determine how many times you are going to need it in the future.
Yeah, actually.
Yes. Good.
Yeah, I mean that when this situation happens, that how the framework can handle this.
Excuse me.
I mean that when this situation happened, that how the framework to improve this situation.
You know, that's a very good question. So basically, for instance, if you use something like Python, and I think you can also use in Java, you can easily see when the object is out of scope. So if an object is out of scope everywhere, you can garbage collect it, right? Because Python it's implementing reference counting, right? But it's implementing reference counting on each kind of instance, right? So if you look at all the instances which kind of refers the object, and I'm talking instance workers, functions, actors, and if you at all of these entities is out of scope, then you can delete it. You can garbage collect it.
Yeah, actually, for some specific situations that if you just expand the OSTM network, I mean that in the NLP neural language processing or something like that, you have to expand all the network once. So in that situation, that your network is not only determined by your program but also by the data. I mean, in that situation, that maybe all the object cannot be determined. Okay, maybe.
Yeah, maybe we should take this offline. I need to see the example.
Okay.
Right.
So let's go to the second question. That's how the interactive with the I say maybe the GPU memory or the FPGA memory for the specific tasks.
How interactive?
How they interactive?
Oh, how it interacts with the GPU? Is that the question?
Yeah.
So it's again the like for instance, you can have libraries like TensorFlow and so forth, or PyTorch, which uses a GPU, or you can write your own, and then you can execute that, say, if execute actors or a function, which includes that library, which run on the GPU. You are going to say that function or actor should run on a GPU. So basically, what Ray provides you is a mapping. Right, it's going to make sure that the function will run on the nodes which have the resources required by your computation. And you can also allows you to do many other things, like I mentioned that you have pretty good control on the scheduling. You can do affinity or anti-affinity. You can say these two actors should run on the same node because maybe they exchange a lot of information between them, or we should run on different nodes because I want to do load balancing. You can do all of these things.
Oh, okay. Thank you.
Thank you for your nice talk. I have one question. When designing a general purpose framework, you have to based on a host language, and I think Ray is primarily based on Python, right? So there's a trade-off between the programmability or easy to use and the performance. As we know, Python has a not really good performance. So my question is, how do you think the trade-off between the programmability and the performance, and which of the two do you think is important?
The answer is depend. Huh? It's a good question. So I think first, let me just make, Python, it's like, it's not that my favorite language. So we are very pragmatic on picking Python as an API because it was machine learning and, everything is in Python. So you have to do it. I will also make a pretty general comment about Python. Yes, Python is slow, but one of the reasons that Python is so successful is because it has very good integration with very high performance libraries, right? NumPy and so forth. There are, or TensorFlow and so forth. They provide, API, Python API by default. So we need to be careful there about when you say Python is slow. Actually, yes, but Python is like, ducting, it's like the ducks between very fast libraries performing computation. So that's one answer to your question. The other answer is that actually, again, all the backend and every, it's written in C++, right? So that can be, it's fast, quite fast. And the final is that we are looking to have APIs for Java and for C++. So if you really want performance at some point, you are going to have C++ backend, C++ API.
Okay, so user has the option to use C++ and gain the performance of C++?
Yeah, that's the plan. That's the plan.
Okay. Thank you.
But it's again, I think we should see the fact that, in many cases, the convenience, easy of programmability and so forth are so important. We should keep that in mind. I think that, it's people really love that.
We have time for one more question.
Is that here?
Hi, Professor Stoica. It's very interesting talk. I'm Jidong from Tsinghua University. I have two questions. The first one is, I think you have talked about the Ray. I think Ray is more focused on the reinforcement and the learning application and also real-time application. So my first question is that, currently we have a lot of different framework. For example, for the Hadoop, Spark, and also we have for the graph application, we also have Power Graph and Preview, a lot of framework. So my question is that, do you think in the future, maybe do we need a uniform framework for the different scenario? So this is the first, okay. Okay, the second is a general question because my group also do a lot of system work. Currently a lot of people working on the system and also doing do the AI system, for example. So my question is that from your point, what do you think the fundamental challenge for the current AI system?
For what?
For the AI application, do you think is there some fundamental challenge from the system side?
From the system.
Okay, thank you.
So the first question is about what is the future? Is going to have still specialized hardware, you are specialized software frameworks, or you are going to have some more unified frameworks? I do think that when things are going to stabilize, when things are going, we are still in this period of 1,000 flowers bloom. We are going to see more unified systems. I have little doubt about that. It's a huge advantage in having a unified system. It's basically you need to learn one system, you need to learn one API. And it's much easier to build an ecosystem, right? I think we are going to see this more and more. Now, and this is what happens in many areas before. It happens with the operating systems. With the operating system, you have a general purpose operating system. When I was doing my PhD, with the network, the same. You have IP, right? And when I'm doing my PhD, you are the people talking about quality of service. You need absolutely need quality of service in networking. You need ATM, right? It's whoever remembers about ATM. You know, people want to, that's they're saying I want to have telephony over the internet. We have to build a new network because this is not adequate. It was for operating system was a lot of real-time operating systems, right? How many now know about, can you name real-time operating systems? Actually, the only one even I can remember is QNX. QNX, which was bought by BlackBerry. Do you remember BlackBerry? Anyway, so that's what it is. So it's a huge, and before the Moore's law ended, think about the Intel, right? So you are going to have a unified system, everything being equal. A unified system is enormously powerful, right? Here is another example. You guys, like Volkswagen. I was looking at the other day. So Volkswagen is building Audi. There are other cars you don't see here, like Skoda, Seat, all of them. So it's a bunch of cars. They have like 3 platforms or something like that. They have 3 platforms and probably dozen and tens and tens of different models, right? They share that, and so forth. So it's hugely powerful. So I have no doubt that when the dust will settle, you are going to see this kind of unified system. Now, you are going to see only unified systems? No. I mean, if you really the performance is critical or things like that, you are still going to build specialized systems. I was giving the example about cars. If you build a Formula 1 car, yeah, you build it one of a kind. But I think that other than that, you are going to see a unification. It's like you have a network effect much stronger because the ecosystem, because people, they learn one systems, and you have more and more people working on that system and things like that, right? And yeah, like also another example, it used to be that high performance computing, it was Cray, right? Many years ago. Everything was specialized. Network, memory, vector processing, CPU. Today, what is a supercomputer? It's commodity, everything, but the networking, like InfiniBand. And that will change as well, right? I was looking, I think that AWS is going to have, 100 gigabits per second networks. 100 gigabits per second. And they are going to put InfiniBand and all of this stuff. So that's the thing, right? You had a second question about the interesting research in systems. So I think that if you look at fundamentally what are the trends, this is what you see the trends, right? The number of the flops per byte of memory is going to increase, right? So now you can think about what does it mean? It means that you can do more computation for the same amount of data. So I think that, then you trade memory for computation, think about this kind of solutions. Maybe you can recompute things because you have so much compute around. So that's one direction. I think that the other thing you'll see it's like if you think about the trends, it's about also the network will increase faster than the memory. So disaggregated memory or disaggregated non-volatile memory will happen. Of course, I'm talking about throughput. Bandwidth, the latency is still governed by the speed of light. But I think this is a way I would think about. I would think about take advantage because you have more compute. Maybe take advantage of disaggregated memory if you can. And I think this will lead to probably new algorithms.
Unfortunately, that's all the time we have with Professor Stoica today. Let's give a round of applause to his very nice speech. We have a gift for you. Here's the mascot. And do you mind